Let's continue our sequence chapter with our third sequence pattern, geometric sequences. Now, geometric sequences is a sequence in which the ratio of any term to its previous term is constant. So the explicit formula here for a geometric sequence is this. So that's the nth term is equal to the first term multiplied by the common ratio to the power of n minus 1. So now let's label all of our terms or units. So this is the first term. This is the common ratio. And n is the pattern number. The same as usual. Now let's just strengthen our understanding on our formula. Let's get into creating the nth term of a geometric sequence. So for instance, if you have a simple occasion here, so we have 2, 4, 8, 16. We have these 4 simple terms. Now let's see, how do we get the nth term? Simply what we do to all usual sequences is to find the difference. Now when they say geometric sequence, we have a ratio gap. So a ratio gap could also be like referred to a gap which has a constant number that can multiply once again and again and again. So in this case, we have 2 to 4 is times 2, and 4 to 8 is times 2 once again, and 8 to 16 is times 2 as well. So now we know that the constant gap is times 2. So this is our constant we can take. Now it's very easy to apply all of these values to our final nth term. So as I said, we have a n is equal to the first term multiplied by the common ratio power n minus 1. So the first term we have is 2. The common ratio we have here is 2 as well. And n minus 1, let's stay there to make our own nth term. Now let's test this formula we have. It's pretty easy now. As we know, just to get to or test the value, we just simply have to replace n with the proposed value that we have. So let's see. So let's get the third term. So what we do here is simply replace n as 3. Subtract 1 as per the formula. So now let's simplify it even more as we go on. So 2 times 2 power 3 minus 1 becomes 2 power 2. And that becomes 2 power 2 is the same as 4. So this becomes 8. Let's see if this works. And our third term is 8. Let's try our fourth term. 2 times 2 power 4 minus 1. That becomes 2 times 8, which is 16. Let's try if that works. That works. So we can prove that the sequence applies accordingly. Now let's go for a different example. Let's see. Let's take this. 3, 9, 27, and 81. Now let's see the difference between each. So 3 to 9 is times 3, 9 to 27 is times 3, and 27 to 81 should be times 3. Now as we have this, let's go on with our formula. We have an is equal to a1 into r power n minus 1. So an stays here as the nth term. Our first term is 3 multiplied by 3 once again as our common ratio with n minus 1 to be as constant. Now let's apply this formula and see if it really works. Let's test it. Now we have 3 times 3 power. Let's take n to be the fourth term. 4 minus 1. So that becomes 3 into 3 power 3. 3 into 3 power 3 is the same as 27. And 3 times 27 becomes 81. And this is what we're getting as our fourth term. Let's go backwards and let's test our maybe third term. 3 times 3 power, our third term, minus 1. 3 times 3 power 2. So to simplify this even more, 3 times 9 is our expected value. So we're getting 27. Does this work? Yes, it does. It is 27 as we expected. Now we can prove that this formula works accordingly to this sequence.